Hotel family, welcome to mathematics lesson number 2. In our previous lesson, I provided some historical information on the Egyptian numeral system. This lesson will deal directly with operations with numbers, or what we call arithmetic. Currently, addition and multiplication are taught as two separate topics and with some explanation about their connection. Our African ancestors along the Nile recognized that there is a symbiotic relationship between the two. One does not really exist without the other. This lesson will focus on what is referred to in English and in mathematics classrooms in America as doubling. When we perform arithmetic operations and identify relationships between numbers or calculate, in Middle Nature, we call that process Gem Mek Nefer, or finding the beautiful, or find the beautiful. In this example, which we saw in lesson 1, we see the Middle Nature numeral system, and we see the symbols in this case are written from left to right into the face of the seated netzer. And remember that seated netzer represents the number 1 million and is identified as aha or hehe. So the Middle Nechian numeral symbol is again represented here. This is the system that our African ancestors along the Nile used. It is a base 10 or decimal system, as I explained in lesson 1. And I will be using these numerals to show the examples of the process that's called doubling. You may use the standard number system that you know, which is probably the Hindu Arabic system. Okay, so I'm also going to use my own handwriting and hopefully it will be legible. Uh, if you take notes, you may try to use these same metal nature symbols. I'm not the owner of these symbols. Um, but if you have questions or comments or concerns, please indicate it in the comment section. Thank you. So, just as a reminder, our current decimal system uses place values with a 0 as a placeholder, as indicated on the third line of numerals. Unlike the place value system, Metonetia needs no zeros as placeholders. Okay, so let's get started with our lesson. So we're going to be reading these from left to right, and this is the primary set of doubles. We start with 1, double we get 2, double that we get 4, double that we get 8, double 8 we get 16, double 16 we get 32, and double 32 we get 64. In lesson 1, we encountered some of these doubles as denominators of the unit fraction in the Wajet. So we see the 2, 4, 8, 16, 32, and 64. Again, they appear as parts of the Eye of Heru, which, as I indicated, was a magical eye that was put together by Netjer Jehuti. So just beneath the primary doubles, I'm going to indicate the doubles of 5. We have 5, double 5, you get 10, double 10, you get 20, double 20, you get 40, double 40, you get 80, double 80, you get 160, and double 160, you get 320. Notice in the 320, I opted to indicate that there are three hundreds instead of writing three 100s three times. So if we write the numerals in Hindu Arabic at the bottom of the set of metal netya, and if we look carefully, we can actually see that 1, 2, 4, 8, 16, 32 pattern repeated. And I would dare say the next one is going to be 64. So let's take a look at how the doubling works from a visual standpoint. When I have 7 1s, if I add another 7 1s, I'm going to get 110 and 4 1s, which would give me 14. And if I double that, well, visually that's kind of nice to see because doubling the 10, we get 2 10s, which is 20. Doubling 4 1s, we get 8 1s, so we have 28. The next doubling the 28, again, we're going to get 4 10s, but then we're going to have 16 1s, which would give us 5 10s and 6 1s. If I double that, I'm going to show that in the little cloud below. So I double the 5 10s and I double the 6 1s. So looking in the cloud on the left, I have now I have 10 10s, and 10 10s can be replaced with the symbol for 100, the coil of rope. And in the right cloud, I have double the 6s, which give me one group of 12, which I can use, replace with the symbol for 10 with 2 1s. So my final double looks like. So the final double looks like one group of 100, one group of 10, and 2 1s or 2 units. So if I read the doubles of 7 from left to right now, I have 7, double that, 14, double 14, we get 28, double 28, we get 56, double 56, we get 112, double 112, we get 224. And for that, I say Gem Mek Nefer. Okay, let's use the Meta-Nature symbols to find doubles of a slightly larger number. And if you like, you can write this in uh, Hindu Arabic numerals just to follow along. So we're going to start with 2 10s, 3 1s, which of course, I should say of course, but hopefully we recognize that's 23. So the 3 1s is either written horizontally or vertically. I do believe it's done for appearance and for symmetry. So in this case, when we first start with the 23, I have the ones vertically, but then when I double symmetrically, it looks better if I write the 6 as 3 1s over 3 1s, but it would be the same if I wrote them vertically. So we have 23, double 23, we get 46. So doubling 23, we get 46. When I double the 46, doubling the 40 gives me 8 10s, or that is doubling the 4 10s gives me 8 10s. Doubling the 6 1s gives me 1 10 and 2 1s. I indicated that 1 10 and 2 1s in the red, but that number represents 92. And then finally, when I double the 9 10s, I will get one group of 100 and 8 10s left over, or 8 additional 10s, and then 4 1s. So this relationship between the number 23 and its doubles can be represented either using Medu Neter symbols or Hindu Arabic symbols. Uh, both representations are accurate and true. So another way to represent this pattern or this product of doubles is to show it as the primary set of doubles um, times 23, or in this case, 1 times 23, 2 times 23, 4 times 23, 8 times 23, etc. So if we recognize that relationship with doubles, we can actually use double to find any and all multiples of any given numbers. So looking at this set of doubles, we have 1 times 12, 2 times 12, 4 times 12, 8 times 12, and 16 times 12, which gives us 12, 24, 48, 96, and 192. If I use Hindu Arabic numerals, the pattern would look like this, which are, again, the even multiples of 12. And what we call this is a table. So using this table, if I want to find an odd multiple of 12, such as 5 times 12, I just need to add 1 times 12 and 4 times 12, because 1 and 4 is 5. So looking at the Merunetya, one group of 12 is 12 and four groups of 12 is 48. If I combine those together, I'm going to get 6 groups of 10. And if I write this the way we would do this in algebra class, we would have 1 plus 4 times 12. And using what we call the distributive property, I would get 12 times 1 is 12, and 12 times 4 is 48. And so that would give me a total of 60. In algebra classes, this property is identified as the distributive property of multiplication over addition. And if I were to write this with variables, I would write parentheses a plus b, close parentheses, times x is equal to a times x plus b times x. Again, this is identified as the distributive property of multiplication over addition. Okay, I'll give you a few seconds to identify this product. One way we would identify this is 7 times 12, and the product of 7 times 12, 84. So if I want to show this using the distributive property and using the Hindu Arabic numerals, I could write this as parentheses 1 plus 2 plus 4, close parentheses, times 12. Usually we combine the 1 plus 2 plus 4 and simply write 7 times 12. Okay, let's see if we can find the product of 12 and 15. We could use the same set of multiples, and if you like, you can pause the video and try to find this product on your own using Hindu Arabic, or you could try with the Medu Netia. So one way to get the factor of 15 is to add the 1, the 2, the 4, and the 8, because that would give you a total of 15. And therefore, we would have to add together these multiples, which is 12, 24, 48, and 96. And so the sum of these multiples would give us 180. The typical method is shown. It is a partial product method, and I would think most of us remember it, even though they do something a little different currently, but it's the same idea where we multiply the ones times the ones, and then the ones times the tens with regrouping, and we have partial products of 30 and technically 150 because we moved the 15 to the left, uh, putting it in hundredth place, and then getting a final sum of 180. Here's another option for finding that same product. Take a moment to explore this strategy. In this application, what we're using is 16 minus 1, or 16 take away 1. The same distributive property also works here. So in this case, if I have 16 minus 1 times 12, it's the same as 16 times 12 minus 1 times 12, and we get the same results of 180. So to demonstrate what we call the commutative property of multiplication, I will use the following relationship. In this case, we're going to use the multiples of 15 to find 12 times 15. We know that 4 plus 8 is 15, so we'll look at 4 groups of 15 plus 8 groups of 15. The 4 groups of 15 is 60. The 8 groups of 15 is 120. So when we combine the 60 plus the 120, the sum is 180, or 6 tens plus 100 plus 2 tens is 100 plus 8 tens. So in this example, I'm going to look at 7 times 32. For this particular case, we can simply create a table that looks at the doubles from 1 through 32, because 32 fits into the set of doubles starting from 1, 2, 4, 8, 16, and 32. And I simply have to align that with the doubles of 7, which is 7, 14, 28, 56, 112, and finally 224. So the product of 7 times 32 is 224. So that brings us to the end of lesson 2 on Egyptian mathematics using Medu Netia. The next lesson will focus on using doubles to find the relationship which identifies the quotient of two numbers. D Ankh Mi Ra. Subscribe, like, share. Shem Hotep.